Hi everyone. So today we're going to be talking about chapter A1.4 on air pollution and population exposure. So let's get into it. So first, we're going to do a little chapter overview, then we'll get into the theory, and then the practice will be in other videos. To access the chapter in the book, you can access this link here, and then you have the link to the full book here. So what's the goal of this chapter in particular? So if we just start with a bit of context, um, air pollution is considered to be the third largest global risk factor for death, following high blood pressure and smoking. And according to research by Murray Al in 2020, it poses a serious threat to public health worldwide. And when you think of its scale and its impact, air pollution can be described as a global pandemic, and it demands urgent attention and monitoring, as just like we did for COVID-19. And this raises the question of how can we effectively do this? How can we effectively track and address this kind of issue? And so there have been many advancements in remote sensing and cloud computing. And because of this, we can monitor air pollution more effectively. And the tools that this provides us, and that we'll look at today, with valuable data that we gain, that can help us understand and respond to air quality changes. So the focus of this chapter is that we're going to be analyzing gridded air pollution data from the Sentinel-5P satellite. Specifically, we'll look at how air quality has changed because of COVID-19 lockdowns. And our analysis is going to cover two components, changes in nitrogen dioxide concentrations. And we're going to examine how those levels can fluctuate over time, especially during those lockdown periods, how they fluctuated over time. And then we're going to do a population-weighted NO2 concentrations. So we're going to quantify NO2 concentrations for specific administrative units, and consider the population density. And with that, we're going to try to understand the impact on different communities. So basically, in the end, the analysis that we're doing is really assessing the changes that happened during COVID-19 lockdowns, with regards to NO2 concentrations, and then we're going to quantify the impacts that that has on population density based on specific administrative units. But as we get into it, it'll become more clear. So what you can expect from this analysis is that we're going to try to understand Sentinel-5P data. We're going to quantify changes in air pollutant concentrations over time. We're going to generate a split panel map to compare two different times. And we're going to calculate population-weighted air pollutant concentrations. This is assuming that you know all of these things beforehand, and this is going to be found in all the previous chapters, which are outlined here. So when you go to the slides and you see this, make sure that you're comfortable with this, because you need to be able to create a graph. You need to know how to import images, image collections, filter them, visualize them, which is like one of the first parts that the book shows you. You need to know how to perform a basic image analysis. So selecting bands, computing indices, creating masks. For example, you want to mask out cloudy pixels. Then you need to be able to use the reducer functions, which often are used in most of the chapters because this really allows you to summarize pixels over an area. You need to know how to write a function and map it over an image collection, mask cloud, as I mentioned, and other undesired pixels, and be aware of designer user interfaces for an Earth Engine app, which is in chapter F6. So all of these things are important to know because I'm not going to go into much detail. So if you assumes you know how to do this, and I'm assuming you know how to do this. So with that said, let's get to a bit of the theory just so we can get a bit of context on everything before we start. So first we can start with air pollution because we're going to talk a lot about it today. And for context, what is air pollution? What are its health impacts? How can we monitor it effectively? Basically, air pollution is generally defined as any substance that alters the natural composition of our atmosphere. And that includes chemical, physical, biological agents. There's many key pollutants that are particularly concerning, and there's particulate matter, PM2.5, there's carbon monoxide, ozone, nitrogen dioxide, sulfur dioxide. And these are important because these are pollutants that can have severe health consequences. Like, for example, particulate matter are tiny particles that can penetrate deep into the lungs. And so that's why they're quite negative. And so globally, what are the health impacts? Chronic exposure to air pollution leads to more deaths than HIV, AIDS, malaria, and tuberculosis combined. And it accounts for significantly more deaths than all forms of violence. So when you consider it like that, you can see why it would be important to start monitoring or why it would be important to be monitored. Specifically, it's estimated that exposure to PM 2.5, for example, and ozone results in around 4.7 million excess deaths annually worldwide. And the number can vary with estimates ranging from 3 to 10 million, depending on different factors. And exposure to NO2, for example, can lead to about 4 million new cases of pediatric asthma annually. And then you think, okay, what are these sources of air pollution? Which is also crucial because if you want to monitor and you want to minimize, then you need to know what the root is. And research shows that over 70% of the health burden from air pollution comes from human activities, which produce anthropogenic emissions. So you've got industries, vehicles, power generation, agriculture, household combustion. These are all human activities um, that create anthropogenic emissions. And then there's also natural sources like desert dust, forest fires, or certain regions that experience more volcanic eruptions and so on. There's also natural sources, but most of it will come from human activities. As I mentioned, 70% of the health burden comes from air pollution from human activities. Then I mentioned earlier COVID-19, and we're going to look at the changes with COVID-19 lockdowns. And the reason I'm talking about this is because COVID-19 was a great opportunity to view changes in air quality. Because people are on lockdown, this reduced the transport and the industrial activity, and global air pollution actually significantly dropped. And during the first 5 months of 2020, when it all really exploded, the decline led to about 49,000, 49,900 avoided deaths and 89,000 fewer pediatric asthma emergency room visits. So that's why today we're going to be looking at those changes and, for example, the relationship with population exposure to see what that looks like on a map. And this comes with, being able to now monitor air pollution and air quality and et cetera. And there are challenges, however, with this kind of monitoring because we have advanced monitoring networks, but there's a lot of regions that still lack sufficient air quality monitoring, and that will limit our ability to manage air quality effectively. So to do this, satellite remote sensing is becoming more popular and accurate because satellites can monitor the atmosphere from many kilometers above the Earth. You can see here from NASA. The only thing is that there are limitations of satellite data because satellite measurements will not necessarily fully represent ground level air quality. So if we rely only on satellite data for health applications, it's not recommended. So some kind of effective methods, for example, would be to combine satellite data with ground-based monitors and atmospheric chemistry models to be able to estimate ground level pollutant concentrations accurately. So it's really about combining satellite data and ground monitors to really improve accuracy, which then after that improves public health assessments. So that's kind of the background on understanding air pollution and how it affects the population and what are the limitations and challenges to monitoring before we actually get into looking at the COVID-19 lockdowns, the NO2 concentrations, and kind of what that relates to in terms of population and some weighted calculations. What's important to know is that air pollution remains a significant global health threat, but because of advancements in monitoring technologies, we can better understand this and address this issue over time. So we're going to start with the practice in the next videos, but first you can add the book's code repository to the code editor by entering this link. And all of the book scripts are available in the panel. And we're going to look at that because in the practice scripts, I'm going to copy paste from the checkpoints that we need into a new script, which I really recommend doing if you want to work on a script because we can't really touch these. It's best not to, so it's best to copy paste as you've probably done with other chapters. So let's get into it. So welcome to practice. We're going to go through section 1 for this first video. And so it's really about data importing and cleaning. We're going to load the satellite data, define an area of interest, center the map, import our population data sets, look at different data sets for population for the Hubei province, import the tropospheric NO2 data, mask out the cloudy pixels because that is not useful when you're trying to look at air quality. And we're going to output a median image from March 2021. This is the population density, and then this is our last image. So these are the results we should be getting today. So first thing we're going to do is go to our checkpoint, air pollution in applications. We've got our checkpoint A, 14A. We're going to copy and then we're going to paste. I'm not going to paste because I had to do a few modifications, but this is what we're going to do for the next ones. So there's a range of satellite-based data sets on air pollution to choose from in the catalog. So I've outlined a few here, but there's the MODIS and the Advanced Very High Resolution Radiometer, which is AVHRR. And so those two are for monitoring aerosol optical depth, so proxy for PM 2.5. And then there's the Total Ozone Mapping Spectrometer Ozone Monitoring Instrument, so Thomson OMI here for monitoring ozone. And then there's more recently the Tropospheric Monitoring Instrument, TROPOMI, which I'll talk about in a sec because we'll be looking at that one. And that's on board of the Sentinel-5 precursor satellite, which monitors a range of different air pollutants. So you can see that in the book as well, but we'll see there's a lot of different ones that will pop up when we look at that. And so we're going to use Sentinel-5P in this practice, but the methods that we're going to look at here can be transferred to these different data sets that I mentioned earlier. Okay, so let's load. For example, we're going to start by searching TROPOMI. So as you can see, there's a range of data sets from Sentinel-5P, which are all super important and can be used for quantifying air quality. Even though Sentinel-5 was launched in October 2017, the data available for analysis is from July 2018 onwards. So TROPOMI, so as you can see, look, you have methane, carbon monoxide, nitrogen dioxide, and so on. TROPOMI, which is the sensor on the satellite, is a spectrometer that senses ultraviolet, visible, near infrared, and shortwave infrared wavelengths to monitor NO2, O3, which should be in here, methane, formaldehyde, CO, and SO2 in the atmosphere. So the swath width of TROPOMI is about 2,600 kilometer on the ground. And that gives you a global daily coverage with a spatial resolution of 7 by 7 kilometers. So all of the Sentinel-5P data sets, except for CH4, have two versions. There's the near real-time NRTI, as you can see here, and then there's the offline, the OFFL. So methane is available as offline only, as you can see, but the NRTI assets cover a smaller area than the offline assets, but they appear more quickly after acquisition. So you have NRTI that covers a smaller area but appears more quickly after acquisition, but then you have the offline assets that have a delayed availability. But each asset contains data from an entire orbit, and it's easier to work with for retrospective analyses. And so we're going to use the offline NO2 product, which is this one, because we're reviewing data from COVID-19 lockdown. So we're looking at some observations of database records. So before we get into this, we're gonna define an area of interest. So Wuhan is pretty famous for being the epicenter of COVID-19 pandemic, and it has witnessed severe lockdowns. So we're going to test to see if we can detect a reduction in NO2 during the early 2020 lockdowns in the surrounding province of Hubei. So To start with this code, we're going to import a global data set of administrative boundaries, and we're going to filter them for intersection with the geometry point object, which is this point here that appears under the import section at the top. So when you copy paste, you're going to copy paste this as well, because this is where the import starts. You're going to need this point to then filter the bounds to the geometry. So this point is important because it's been drawn with the drawing tool here, which means that you need the coordinates. And it can be moved to a new location to rerun the analysis for that administrative boundary, which is what we're doing. So this is what we're going to use after this. We've imported, we have the geometry, then we're going to center the object, which you should already know from previous chapters. It's one of the basics. And then we're going to set the options hybrid. It's just setting the display as a mixture of normal and satellite views. And once you've centered the map on Hubei province, we're going to import, well, you're going to add the layer, but we're going to import the population data set. And this is going to be helpful for calculating our population weighted exposures in section 3, which we're going to look at later. And we're going to use this data set, which is the gridded population of the world version 411. And this is going to be for 2020 and includes a total population count per 1 by 1 kilometer grid. Okay, so in the book, there's also a question when you go through this, and there's other population data sets of gridded population, and they ask you to search them and then compare them and say, which one looks more realistic in your opinion. I'm not going to go into too much detail because that's kind of up to you to go through that, but I'm just going to show you what you can look for. So basically, in this code, all I've done is that I've restated the variable. I've literally copy pasted this twice, added a different number just to make sure for me that I know what's happening. And then repeating that here, just adding 2, 3, corresponding to the two data sets that I've added. And then you're going to have to adjust this because in the original script, it's at 400, I believe, 4,000. If you leave it at 4,000, for these two, it's not going to show up. Then after that, you can add the layer based on what you created here, and then you can see what happens. So just think about how these show up. So for example, you have here the gridded population we're using at a maximum of 100, which is obviously way too small for this data set. And the higher, the brighter will mean that there's a higher population count. And then you've got the world population data set. So you can compare them. But then what happens if, we put it at 4,000? What can you expect to see? Nothing appears. So anyways, you can play around with that. But I just wanted to show you what happens if you work with these different data sets. So now we're going to import the NO2 data. And like the optical satellite data, there's going to be things in the atmosphere that will contaminate the signal from the object or chemical you want to measure, which in this case is the NO2. So as I mentioned earlier, we're going to get our Sentinel data. So it's going to be the offline one. And then we're going to define the function to basically create mask, because clouds are a common issue for land surface reflectance products, as you remember from chapter 4. And they're also an issue when you're trying to measure air pollutant concentrations. So here we're going to create a mask, and it's just, you should have seen this in previous chapters, but you create a function to mask out the pixels with a cloud fraction. In this case, we're looking for above 0.3. Well, that's 30% cloud cover. And we don't want anything above that. And so you can test different masking thresholds to see what, works best for you. Maybe you need to keep everything under 10% or 20%, although, note that the more you mask out, the more constraints you put also will limit the data that's available, because some data sets will be affected by clouds no matter what. And then after masking out, we are going to create a median composite from images during March 2021. And we're working with the band that gives measurements for the tropospheric vertical column of NO2 here. So you have to select it. Because if you look at this data set, for example, in your bands, you're going to want to select this one. And we're not using the stratospheric or total vertical column. And this is because the troposphere is the closest we can get to ground level measurements with Sentinel 5P. So then we're going to run it and we're going to get the immediate image for March 2021. As you can see, we're selecting March 2021. We're clipping to our geometry or our collection. And then we're going to visualize it. So we have our colors here. Now I've already run it a few times because of the population data set. And then this is what it gives us. So as you can see here, it's the color gradient that we're getting. So there's a bunch of red, and then it kind of goes in from hot to cold. So the hotter colors are going to mean higher concentrations of NO2, and then the more you get into the blue, it's going to be lower concentrations of NO2. So now you have an idea. We're just starting off. We're just putting our data, but you have an idea of what's happening. What you can do too is because the most important part of these labs is really to understand the data you're working with. If we look at our gridded population, um, let's say we reduce opacity. You can see, okay, the hotter colors, are they more associated with the population data is? If you're looking here, you have really dark colors, which means lower NO2 concentrations. And then here, remember, there's very bright colors, which means you have population counts of 4,000 or above, because remember our max. So, you can really look at trends already happening just from this basic image. Now we're going to go into section 2, and we're going to look more in depth, and we're also going to create a split panel map and just look at our images and our data more in depth. So that is going to be right here.